Hello everybody, this is Mr. Straker back again for another Algebra 1 video. Today's topic was section 2.3 in our student journals. Now, normally, I'm going to be honest, I'm not the biggest fan of the explorations in this book. I feel like they take too long and they don't give you enough. This exploration's a little bit different. With the class, we actually worked on two problems together. We worked on 1A, and we compared it all the way over here to 2A on the next page. So with these tables, it says to complete the table, that's step 1. Decide which graph represents the solution of the inequality 6 is less than 3x. So we need to look at these two graphs, and after filling in the table, decide which one of them best represents the information there. After that, our goal is to write the solution of the inequality. So, let me give you an example for how we fill out this table. Up here in the top row, we have all of our x's. These are just all of the numbers that we're expected to plug into our inequality to see if it works or not. This row is telling us it wants 3x. So, we want to take each of these numbers and multiply it by 3 to get this one down here. So for instance, if I took the number 4 here, x is 4, so 3x is 3 times 4, which means we're going to put a 12 in that box. You're going to want to do the same for all of these on both tables. Last but not least, this is some weird notation, but it's basically asking us, hey, is 6 less than 3x? Since we found 3x in this row, figuring out if 6 is less than 3x should be an easy breezy task. Here, we ask ourselves, is 6 less than, well, 3x in this column was 12, so is 6 less than 12? Yes, 6 is less than 12. So we write down yes here. What I'd like you to do is I'd like you to pause the video, try filling in these tables for yourself, and come back once you do. And if you just want to skip to the next part, you can, but make sure these tables are filled in because we're going to be having some intense discussion about them. All right. Hopefully we had a chance to finish up. If not, let's take a look at what we've got. So, for the 3x row, what do we notice? We start at negative 3. And since we're looking for 3 times x, 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6. We're really listing all the multiples of 3, starting at negative 3 and going up to 15. From here, we should also notice that, well, all of these numbers are very much less than 6. Negative 3 is, 6 is not less than negative 3, 6 is not less than 0, 6 is not less than 3. So that's why I wrote no, no, and no. On this other side, 6 is less than 9, 6 is less than 12, and 6 is less than 15. The middle term here, is 6 less than 6? Our answer should also be no. 6 isn't less than 6, 6 equals 6. So no, 6 is not less than 6. On the other table, we should have written out the following. Since we're doing negative 3 times negative 5, for instance, we get positive 15. Negative 3 times negative 4 is positive 12. 9, 6, 3, 0, negative 3. Likewise, we ask ourselves, is 6 less than these numbers? Well, 6 is less than 15, it's less than 12, it's less than 9. 6 is not less than 3, it's not less than 0, it's not less than negative 3. And like we mentioned last time, 6 is not less than 6. So this is why our tables look the way they do. I want you to pause again real quick. There's going to be a lot of pausing in this exploration, and I want you to come up with 3 things that are either similar or different across both of these tables. So just pick out 3 things, no matter how mundane they seem, or no matter how normal they seem, any 3 things you notice about these two tables. Pause the video here and think about those 3 things. Did you get a chance to think? Well, let's take a look at these two tables and compare them side to side. Might need to zoom a little bit, but we'll make it there. There we go. Some of the things you might have noticed. Well, we're kind of using almost the same numbers here. -1, 0, 1, 2, 3, 4, 5. The difference is over here, we turned all of them negative. So they're kind of facing the opposite direction. It's the same thing with this second row. This one counts up from -3 to 15. This one counts down from 15 back down to -3. Of course, these numbers are exactly the same, just flipped. These ones were also turned negative. That comes from the fact that on this one we were looking for 3 times x, on this one we were looking for -3 times x. There might be other similarities or differences that you found, but these ones are the ones that are most related to what we're going to discover in this section. So, from here, we need to figure out which of these two graphs represents this table, which of these two graphs represents this table. To figure this out, anytime you're doing almost anything with graphs and figure out where the arrow goes, I always recommend plugging in numbers. First of all, there is a number on here that wouldn't be very helpful for us. Can you spot it? That number is 2. Notice how on both graphs, 2 looks the exact same. We have an open circle because we have a less than symbol in our inequality up here. And we start at 2 for reasons that we don't really explain. This is something that you'll have to figure out after we figure out which graph is which. But let's get back to that later. For now, I want us to look at these two graphs. The left graph has all of the solutions pointing to the left. That means that 1 is a solution, 0 is a solution, -1 is a solution, -2, if it was on here, would be a solution. It keeps on going down. On the contrary, this one has solutions going up. This says that x could be 3, x could be 4, x could be 5, and so on and so forth. To compare this with the table, let's pick a number. We always just want to pick a number, and it usually doesn't matter which type of number we pick. I'm thinking in my head the number 4. Let's look at our column 4. We said that when x equals 4, 3x became 12. And since 12 is greater than 6, we said yes, 6 is less than 12. What this means in a graphing reasoning is that 4 is absolutely one of our solutions. Any number that is a solution, which means for this it has a yes on it, must have the arrow going through it at some point. So which one of these two has the arrow going through 4? It's got to be this right one. Again, our arrow goes through all of our solutions. But we're not quite done yet. There is one last step. That is to write the solution of the inequality. As a reminder, a solution of an inequality is what you get when you just have x by itself. Unfortunately, in our equation, x is not by itself. But do you have any ideas, especially based off what we learned in Unit 1, for what we could do to get it by itself? If we have 6 is less than 3x, and we want to get the x all by itself, because that's what happens when we have a solution, what's stopping it from being by itself? Well, it's this 3. How is this 3 attached to our x? Since it's next to it, it's being multiplied. Well, now this looks familiar. How do we get rid of multiplying by 3? This is where we divide by 3. But did we ever just do it to one side? I don't think so. We always divide by the same thing on both sides of what was once our equal sign, but is now an inequality symbol. If we do this, take a look at what we're left with. X is by itself, so we know we did it right. We have our inequality symbol facing the same way, and 6 divided by 3 is 2. So the solution is 2 is less than x. It can sometimes be hard for students to conceptualize this, but you are always free to flip your whole equation the other way, making it instead look like x is greater than 2. Is this situation represented by the graph? Well, yes. 2 is less than x. Here's 2, and all of our x's are bigger than it, so 2 is less than x. You might not have needed to solve this way to figure out our solution, though, because as long as you have a graph, you can also figure out your solution. Here's how. Our endpoint is at 2, so we know that we're comparing x and 2. All we need to do now is figure out what symbol goes in between. Since it's an open circle, we know that it can't be equal, so it's going to be either less than or greater than. Now we just need to figure out which one of those it is. To figure it out, I always recommend the good old-fashioned plugging it in trick. Our arrow passes through the number, let's use 5 this time. Since it passes through 5, if we were comparing the numbers 5 and 2, what symbol would we put in between them? 5 is bigger than 2, so we use a greater than symbol. That means that x is greater than 2 because our arrow represents all the things that x can be. Either method will give us the answer. What I'd like you to do is I'd like you to try that same logic here on this table and these graphs. Figure out which graph represents the situation and decide how you want to solve the inequality, whether you want to solve it with an equation or solve it by analyzing the graph. Take a minute, pause the video, and do it now. Well, at this point, if you were walking through all these activities, you must be pretty exhausted pausing the video, but don't worry. This is how explorations work. It's meant for you to do before you really know too much of anything. It's meant for you to try on your own. So, as we're analyzing these graphs and we're looking at the situation, something's a little different. First off, our endpoint is not at 2 anymore. It's at -2. From here, we need to figure out which direction our arrow should face. Well, our solutions that we had yes for were -3, -4, -5. That means when x is -5, the solution works. When x is -4, the solution works. When x is -3, the solution works. So we want our arrow to go through -3, -4, -5. You could think about it the opposite way too. You could say to yourself, well, -1 doesn't work because 6 is not less than 3. 0 doesn't work. 1 doesn't work. So that means our arrow should not go through -1, 0, and 1. Either way you do it, you'd find that this left graph represents the situation. It goes through -3, -4, -5, all the things we said yes on, and it doesn't go through any of the things we said no on. The -2, it still kind of doesn't go through. We have an open circle to show that -2 is still not a solution. So at this point, we need to figure out what the solutions are. And this is the reason why I like this exploration. Because depending on how you decided to do it, you may have been deceived by Mr. Strager once again. Let me show you what I mean. If we have the inequality, 6 is less than -3x, how would we solve this for x? Well, the -3 is attached to our x, and just like the last one, it's being multiplied. So to get rid of it, we would divide by -3. So surely, when these cancel out, we would end up with the solution, -2 is less than x, right? To anybody who did the graphing method, you might say, Mr. Strager, that doesn't look quite right. And to those of you who did the equation method, you're going to look at the graphing method and say, hold on, that doesn't look right either. if we look at the graph, we know our endpoint's at negative 2. So x and negative 2 are being compared. We need to figure out if x is less than negative 2 or x is greater than. So let's plug in a number. I want to choose 0. If we're comparing 0 and negative 2, well, 0 is less than negative 2, right? But here's the catch. 0 isn't on our number line. So we wouldn't want to write down 0 is less than negative 2. That would mean our graph has to go through this way. So instead, we go the opposite direction of what it should be. And we say that x, oops. Sorry, I apologize. I totally got mixed up there. Normally we would say 0 is greater than negative 2. But we don't want to say that because then our arrow would be pointing through there. It'd say that 0 is a solution. Since 0 is not a solution, we want to do the opposite and write down this sign. Of course, you can avoid that whole confusion just by picking a number that's actually on the line, like I mentioned you should. I just wanted to show you what would happen if you picked another one. If we compared negative 4 and negative 2, it's on the number line, so we're looking for a true statement. Well, it's true that negative 4 is less than negative 2, so x should be less than negative 2. These two answers, despite looking very similar, are actually opposites. This one says x is less than negative 2. If I flip this and rewrite it, this says that x is greater than negative 2. So what's the deal? Well, the deal is negatives are weird. Sort of the easiest way of putting it. Let me give you an example. Here, I magically apparated a number line that goes from negative 2 to 2. Let's pretend for a moment that we have x is greater than 2. Or sorry, greater than or equal to. That's why I have the closed dot. If it's greater than or equal to, it'll surely go in this direction. X could be 3, 4, 5, 6, or a million. Here's the problem. Once you have a negative involved, when you divide or multiply by a negative, the entire other side becomes negative. So if our equation was negative x is greater than or equal to 2, then we have a problem. When we divide by the negative, this would become negative 2. But it wouldn't make sense for us to put a dot here and to have our arrow continue the same way. Keep in mind, we just flipped our whole equation basically by dividing by a negative. If we went the same way, we'd have all the same solutions, as well as just some extras. It'd almost be like we're getting more solutions than we started with. And a negative isn't that powerful. To show the flip that happens when we divide or multiply by a negative, we're also going to have to flip our arrow the other way. That's why, when we were comparing these two activities, our first arrow was pointing towards the right and was at positive 2. Our second arrow was pointing towards the left and was negative 2. And all we did was we put a negative in there. That's all that changed. Because of this, anytime you multiply or divide by a negative, not only do we flip from positive to negative, but the direction of our arrow, or the direction of our inequality, also reverses. So if in this example I divided by negative, I would have to flip it the other way. Greater than or equal to becomes less than or equal to. It's weird to think about, but as long as you remember the rule, that's what matters. Speaking of the rule, let's figure out what that actual rule is. So let's flip over to page number 40. Of course, these pages are very thin and bleed through, so I apologize, but in your own student journal, you should be able to see this as well. In your student journal, you'll see that it reads out two different rules. One for when c is bigger than 0, one for when c is less than 0. We're not going to talk too much about the formalities of what c is, but if we had something like a, b equals D, oops, sorry, I apologize. Let me rewrite this. If we had something like AC equals D, imagine these are all numbers and variables, and we wanted to get A by itself, we would divide by C. The C in both of these represents the actual change that we're making to our equation. It represents this step. So if the number that we're multiplying or dividing by is positive, we solve it like we did in Unit 1. You can read that in the words here. Multiplying or dividing by the same positive number produces an equivalent inequality. It's the same deal. So if, for instance, we flipped over to page 41 and looked at number 1, 6x is less than negative 30. To solve, we want to get x by itself. So what would we do to both sides to get x by itself? If you said divide by 6, you're right. And the rule is, if we're dividing or multiplying by a positive number, we solve like normal. So we just divide like 6, just like normal. We keep our sign the exact same. X is less than negative 5. I want you to try to graph this, so I'm going to pause the video again. I know I said that was the last pause. I lied and tricked you again. Mwahaha. Pause the video, try graphing this, and check your answer with me. How'd we do? If your number line is flipped around, where your 0 is down here and your negative 10 is over here, unfortunately, that would be marked incorrect because we want to make sure our number line always goes in order from least on the left to greatest on the right. Negative 10 is the lowest, so it has to be all the way over here. If you did a closed circle instead of an open circle, let's remind ourselves that a closed circle is only used when we have a symbol like in number 2, where we have an equals bar underneath. If your arrow was pointing the other direction, well, let's test out a number together. Pick a number. We'll see if we get the same one. I'm telling you right now, I picked negative 2 off the top of my head. Let's test it out. Let's plug in negative 2. Is negative 2 less than negative 5? Well, no. Unfortunately, in negatives, the more negative you get, we consider that to be the lower number. So negative 10, for instance, is lower than negative 3. So, no, that doesn't work. That means our arrow cannot go through negative 2. It has to go the other way. Well, that's how it works for all problems like this. So even if I had something like x divided by 5 is greater than or equal to 2, what would we do to get x by itself? We would multiply by 5 because to get rid of dividing by 5, we multiply. Our answer would be x is greater than or equal to 10. We don't do anything else because the rule says we're fine just solving it as is. Of course, with every rule there is an exception. The exception in this case is here, when c is less than 0. In other words, if the number that we are dividing by or multiplying by on both sides is negative, we've got some problems. The notes say when multiplying or dividing each side of an inequality by the same negative number, the direction of the inequality symbol must be reversed to produce an equivalent inequality. That's why the graph for this one, on number 2, had the correct solution. X is less than negative 2, but our equation said x is greater than negative 2. When you multiply or divide, the rule is, since we're flipping over to another side, either negative to positive or positive to negative, you also have to flip your symbol. That's why the equation didn't work out the way we wanted it to. Oops, that's the wrong page, I apologize. So, let's give an example all the way on page 41. Let's take a look together at problem number 4. Well, in problem number 4, we have negative 4 times m is greater than or equal to negative 16. So how do we get m by itself? Well, we would have to get rid of this negative 4. It's being multiplied. The opposite of multiplication is division. And this part right here is where you need to stop and ask yourself, is our c value negative? In this case, our c value, the thing we're dividing by on both sides, is negative 4. So before you do anything else, flip your symbol so you don't forget. It is the easiest way to get one of these problems about as wrong as you can get it, is forgetting to flip the symbol. So as soon as you see that we're dividing by a negative or multiplying by a negative, don't even write any of the numbers down. Write down the symbol first. Then we can go back and deal with the numbers. These negative 4s will cancel out, leaving us with just m on our left side. Negative 16 divided by negative 4 is positive 4. So, again, try to graph this. We'll come back in just a moment. How do we do on this one? With this one, again, your number line should be facing from least to greatest. Our endpoint is at 4, and it's a closed circle because we have a less than or equal to symbol. And our arrow is pointing in this direction because if we test out any of the numbers in this direction, let's say 0, the inequality becomes true. 0 is less than or equal to 4, so the arrow has to go through that test point, 0. Overall, the main thing I want you to take away from these notes today is, as soon as you multiply or divide by a negative number, without hesitation, I want you to flip that symbol, because that is the only way you'll get these wrong. Of course, you could also get the numbers wrong or something like that, but overall, that is what I want us to remember. That is the end of these notes, everybody. If you want to stick around to watch one more example done, I'm going to be working on number 3. If not, have a fantastic rest of your day. For those who stuck around for this last little example, it's always good to just double check, especially when there are fractions involved. For this example here, we have negative 6/7 is less than or equal to 3 over 7 times f. Well, what's being done to the f that we need to get by itself? 3/7 is being multiplied. So, how do we get rid of multiplying by 3/7? You might be tempted to say, well, 3/7 is being multiplied to f, so let's divide by 3/7. And you wouldn't be wrong, you could do this. But look at how messy this looks. It's like a totem pole. They're all stacked on top of each other. Instead of dividing by a fraction, there is an alternative that is much easier. When you want to divide by a fraction, instead, try multiplying by the reciprocal. As a reminder, the reciprocal is the fraction flipped upside down. So the reciprocal of 3/7 is 7/3. Of course, you want to multiply by this on both sides. When you do that, because you have a 3 on top and a 7 on top, a 3 on bottom and a 7 on bottom, they will both cancel out, leaving us with just the f. That's why this works. Before we do anything, are we multiplying or dividing by a negative? No, 7/3 is positive. So we keep our symbol the way it is, just like we like it. When doing a problem like 7/3 times negative 6/7, you could put it in your calculator. But I want to teach you a trick. Anytime you have the same number on the top and bottom of a fraction, you can cancel them out by crossing them out. We have a 7 on top and a 7 on bottom, so let's cross those off. What we're left with is our negative symbol, our 6, and our 3 is on bottom. Well, negative 6/3, we can simplify that to negative 2 is less than or equal to f. The reason why we didn't flip our symbol despite this negative here is because we're not multiplying or dividing by a negative. What we're multiplying and dividing by is this number that we create, not anything that already exists in the problem. So when we graph this, we should end up with our negative 2 in the middle. When making our number line, we want to make sure our lower numbers are here and our higher numbers are here. So we count up to negative 1, 0, 1, 2, and 3, and down to negative 3, negative 4, negative 5, negative 6, and negative 7. It's less than or equal to, and our endpoint is negative 2, so we put our dot here, and it's closed because of this equals bar. To decide where our line should go, let's choose a number. I'm going to choose negative 4. Why not? If we plug in negative 4, we get negative 2 is less than or equal to negative 4. Is that true? Is negative 2 less than or equal to negative 4? Meaning that negative 2 is further to the left of negative 4? No, it's nonsense. That means that we want to avoid putting our line through negative 4 at all costs. So it goes the other direction. Thank you, everybody. Have a good day.